The last thing I'd like to talk to you about today is the behavior of higher degree polynomials. And by higher, I mean higher than 2. Degree 2 polynomials are quadratics. We know pretty much how they behave, and we can do things like solve quadratic equations exactly using the quadratic formula. We can find the max or min. It'll only have one of those two by finding the vertex. We really are pretty good with quadratics, but when we get to polynomials that have higher degree, then we run into some trouble. We don't have a cubic formula, or at least we don't have access to one that we're going to use all the time. In fact, you get so high, there is no formula to solve for at all. So we get a greater dependence then on our graphing calculators until such time that we can get to calculus and maybe learn how to do some of these tricks symbolically. Polynomials of degree 3 and higher pop up. I mean, when we do volume calculations, we're probably going to end up with degree 3 polynomials. Weight is proportional to volume, so they'll pop up there. Sometimes we'll solve radical equations where we have to square or raise both sides of the equation to a power, and higher powers will pop up then. And even some things with circular measure, believe it or not, you can kind of put these together and you end up with some cubics and quadratic and quartics. So it's important that we understand how these things behave, because we're going to have to put them on our calculator, and we have to ask this question then: am I looking at all the interesting stuff? You know, you've just got that little viewing rectangle that you use on your graphing calculator. How do you know that's at the good stuff? There may be something really interesting happening over here that you're just not looking at. So I want to talk to you just a moment about behavior and how to tell if you're looking at the quote-unquote entire graph, all the interesting stuff with a polynomial. The first little trick that we can keep our eyes open for is what's called the fundamental theorem of algebra, which just says that a polynomial of degree n will have at most n real zeros. And if you want to get technical about it, it will have n complex zeros, but we're worried most about those that will appear on our calculator. So here's the degree 5 polynomial, and sure enough, if you'll notice, it hits the x-axis. These are the zeros that I've circled 5 times, right? In fact, you'll notice it has 4 peaks and valleys. You know, that's the most peaks and valleys it could have. But beyond this, I mean, it doesn't have to have 5. For example, if I scaled it upwards, okay, this only has 1 real zero, but you can see if I drew a horizontal line across there, that I could hit it 5 times. And that's what you really need to look for, is how many times could a horizontal line pass this thing? Okay, so that tells me that all the possible zeros are right there. I'm looking at them, okay? Another thing to take into account is in behavior of the graph. If a polynomial is even degree, then it doesn't matter whether we take a big positive number or big negative number and raise it to an even power. You're going to get a big positive number. So as long as the leading coefficient in front of that term is positive, it will stay positive, and both ends will go up like this. It's good, okay? But if that a is negative, it'll take those positive values and turn them down, make them negative. So I just flipped it over, really. If that leading coefficient is negative, it'll flip it down. But if with even degree, they're both going to go in the same direction. Now, with odd degree, different things happen. You take a positive number, raise it to an odd power, it stays positive. That's, let me get this right, here. But if you take a negative, big negative number and raise it to an odd power, it's negative. So you get this kind of John Travolta kind of thing. As long as the a is still positive, it doesn't change the sign. So you're kind of like this. Okay, which is, I think, what I'm doing here. And then if the a happens to be negative, it'll flip it around, and you get things going. You got John Travolta over to this side. Okay, odd degree, different ends. Okay, that helps you kind of spot if you're graphing something that's odd degree, but in your graphing window, both ends are going in the same direction. You need to expand your window. You don't have everything you need to see there. Okay. So let me give you an example. This is just something you could be doing in your workshop or something. Say you want to construct an open box to keep tools in out of a 16-inch by 20-inch piece of sheet metal. And you're going to do that by cutting square corners out and then folding the sides up and welding the creases. So it'll look something like this. Here we go. And of course it would be height X when you do that. Okay. What I'd like to do is worry about the volume of this. If I'm going to build this box, I'd like it to have a nice, as much volume as possible so I can put stuff in there. Well, what you're doing here is you've got the 16 inches this way, and it's pretty, I didn't put 16 there, but that's the short side. And then you're removing x from both sides, so this base would be 16 minus 2x. Okay, whatever x is, this will be 16 minus 2x. And then you've got 20 up and down, and you're taking x away there and there. So this dimension would be 20 minus 2x. And so the volume, length times width times height, is just this. And that's a degree 3 polynomial. That's higher than quadratic, and it could be a trouble if we try to solve equations with that. And just to show you what it looks like, let me first multiply it out and graph it. So this is a odd polynomial. You notice that the endpoints are doing the old John Travolta thing, okay? And then because that leading coefficient, I'm cracking up the camera operators. This is great. The leading coefficient is positive, so it goes up on this side and goes down on this side, okay? And if any horizontal line would go through there 3 times. I could put a horizontal line through there 3 times. So this is all the activity that I want to see in the graph. And then I can do, from that graph, I can do a lot of things. I could say, well, which x are valid? Well, I can't have negative volume here, folks, right? So where this dips down below the x-axis, that's bad. I can only go out here to 8. And then which x gives the maximum volume? Well, until I know some calculus, I just have to rely on my calculator to find that peak right there in the valid range. And then I could ask the question, well, okay, let me set the volume at 400 cubic inches. I can expect 2 answers, and really you can try to find them by factoring. In fact, all these numbers are divisible by 4. I've got my nice divisibility theorems to fall back on. But I don't know how to factor this, so I'd have to rely on my calculator to get those answers. So when you get above degree 2, that calculator is going to be your best friend. It's going to find those answers that otherwise you wouldn't be able to find. Let me summarize what I was just talking about, and I'll be back in just a second.